so the topic here is going to be about the CPU and data moving around, the types of data transmission, okay? And just getting into the basics of that. So the CPU, little bits more about that, okay? The coprocessor, okay? What a coprocessor is, it's a special purpose processing unit that assists or helps out the CPU. So, like a human doing a job, if there's two people doing the job at once, it makes things a lot easier and a lot quicker. So that's the same theory behind a coprocessor. Two processors working at once, two separate units, okay? Not to be confused with multi-core, which I'm going to talk about later on, okay? Two completely separate processors. So by offloading processor-intensive tasks from the main processor, coprocessors can accelerate system performance. So one of the most common ones I see the most common coprocessor I know of is the processing of graphics. Okay, it's very common that a graphics card would have its own type of processor or even its own memory attached. Okay, so graphics is where it's typical. Other operations that might be performed might be arithmetic, signal processing, string processing, or encryption. Okay, yeah.
It's kind of off topic, but what would be better for a gaming? Would be the processor or RAM?
For games?
Yeah.
Or what's more important?
Yeah.
My gut would tell me, you know, a very important, number one, a good graphics card. But if you're buying, buying a machine from scratch, I'd probably say having 64-bit processing, as much RAM as possible loaded up. Maybe if you're thinking about a machine for gaming, I might wait a year to see this trend that I keep referring to, that because of 64-bit processing, the amount of RAM you're seeing in a machine as standard is starting to go up and up. Yeah. Okay, so at the moment your standard RAM is around 6 to 8 gigabytes. Only 2 years ago, maybe it was 4 gigabytes. So to me, the technology that's accelerating at the moment isn't the power of the processor. The processors are getting better, but only slightly better every year. But the amount of RAM is increasing at a great rate. And I would say even within the next 2 or 3 years, the amount of standard RAM that you see in a machine could be up to 50 or 100 gigabytes of RAM. So I'd stop and think about that. Okay. Okay, so from processors to RAM and back to processors again. So a definition of what is meant by clock speed was the next item. So let's take a look at that. Right, so clock speed is also known as clock rate, the speed at which a microprocessor executes instructions. It's being recorded, lads, okay? There you go. You're going up to YouTube, guys. So when the attendance officer calls, we'll know that, right? Clock speed isn't to be confused with your clock or your watch, okay? When you think of a clock, don't think of your watch going off once every second. It's how many instructions can get processed per second is what's important when you're thinking about a clock, okay? So clock rates are expressed in what's known as megahertz or gigahertz, okay? So when we're talking about megahertz and gigahertz, you're talking about how many, when you have 1 second of time, how many of these instructions can take place across that 1 second measurement, okay? And megahertz, when you're talking about those, or hertz is, if I'm operating at 1 hertz, okay? As you can see, okay, we're all dying, okay, but let's live.
We're just dying quicker.
Yeah. So we're talking about, when we're talking about somebody coughing, he's coughing at 3 coughs per second, okay, so his cough is occurring at 3 hertz, alright? Yeah, okay. But a computer is a very efficient machine with a clock rate where we're talking about megahertz or gigahertz. Megahertz being millions of instructions per second, and gigahertz?
Billions.
Billions, yeah. So 1 gigahertz is, that's I said, 1,000 megahertz. So a processor nowadays, compared to one in the 90s, is capable of processing 1,000 times more instructions. Okay, when you're doing a comparison there. The CPU requires a fixed number of clock ticks or clock cycles to execute each instruction. The faster the clock, the more instructions the CPU can do in 1 second. Okay, so that's what clock speed is all about. Okay, I'll just move you on there to cache size. Okay, and we've talked about the cache when we talked for question 1 about the primary and secondary memory, and we looked deeper into primary memory. We did talk about the cache at that stage. So just a little bit of a recap, I suppose, about the cache. So what they do is the only purpose of the cache is reducing memory access by buffering frequently used data. So a fancy way of saying that, it's an extra bit of RAM thrown into the CPU so that you don't have to go talking down your bus line to get to the RAM itself. Okay. Cores. So we talked about a coprocessor earlier. In more modern processors, instead of having 2 or 3 processors, you have processors with many cores, or multi-core processing seems to be the trend that's out there right now. So it's a single computing component. So you have one processor, but inside that processor you have many cores. Quad core, how many processors?
4.
4, yeah. Seems obvious enough there, okay? These units can read and execute program instructions themselves, all right? The instructions are ordinary CPU instructions such as add, move, branch, but multiple cores can run multiple instructions at the same time, increasing the overall speed, okay? So it's called parallel computing, where you're able to do many sets of instructions at once. A dual core processor would be nearly twice as powerful as a single core processor, but in practice, the performance gain is less than a 50% gain. Okay, so in theory, a dual processor is twice as fast, but in practice, not the case. Okay. Okay, so like I said, I'm going to move on to the next slide. If you can catch up, like I said, this is going up on YouTube, and you'll be able to. You'll be able to review the notes here on YouTube and take a look. Bus width. Okay, so the main conversation here about bus width would, I suppose, first of all, hark back to the 90s where 32 gigabyte bus width became standard, but things are changing right now, okay? So the 32 gigabytes were once desired because they could address up to 4 gigabytes of memory, okay? This is very relevant to what Ray was talking to me about, because we had a limit with 32-bit 2-bit systems of 4 gigabytes of RAM being usable. But now, with us moving on to 64-bit processing, the amount of RAM that you can use is pretty limitless, okay? You can see here when I read on, some modern applications require more than 4 gigabytes of memory. So that's 2 to the power of 32 or 4 billion memory locations, okay, to complete their tasks. So 64-bit systems are now becoming more attractive because they can potentially address 4 billion times more locations than a 32-bit.
So what's the difference between like a 32-bit computer that has 500 gigs and 64-bit computer that has 500 gigs?
Well, a 32-bit computer can only address 4 gigabytes of RAM. We're talking about short-term memory. We're not talking about long-term storage of 500 gigabytes. Okay, we're talking about the RAM here, the RAM memory. So a 32-bit system can only utilize 4 gigabytes of RAM. It's not going to make any more use of any more RAM beyond that. Okay, with 64-bit becoming standard, the amount of RAM on a computer is increasing because it can increase. Okay, it was limited before. So that's why I'm predicting to Ray when he's asking about a gaming computer. I'll give you a second to recover there so you can hear me. You good? Okay. When he's asking about a gaming computer, he asked me what's the most important thing, and I said, well, because of 64-bit processing, you're going to see the amount of RAM in computers really just take off. And we have, in the last year or two, it's doubled. You know, your standard RAM in a computer now is up to 6 or 8 gigabytes. That's what I was saying in the conversation there. And I feel it's going to be set to increase really up to 60, 100. You know, that kind of amount of RAM is going to be in computers over the next few years.
So what to do? Just the 64-bit is faster with the RAM than 32-bit?
Well, okay, bus width is your channel, okay? So think of, if you're channeling traffic down a dual carriageway, and you go from a dual carriageway to a motorway, which is 3 lanes, you're going to get more traffic down there. It's going to be more efficient, okay? So So that's like, I suppose, a real world comparison. You can channel more data down there. You can hold more data on a temporary basis in your RAM. So in other words, all these billions of instructions that can be processed, there's no, when they're being trafficked through the CPU and they're held in the temporary storage and they're being shunted up and down the pathways along the motherboard, the buses, this all happens more quickly. Okay, the processing happens even more quickly because of this technology. Okay, since 1995, the second bullet there, when Windows 95 back in the day was introduced, support for 32-bit applications, most of the software and operating system code has been 32-bit compatible. So the problem nowadays, I suppose, or the transition we're undergoing at the moment, while most software is available only in 32-bit, the processors are becoming 64-bit. So if you have 32-bit software, you're not getting the benefit of your 64-bit processor. Okay, it's only again in the last year or two that 64-bit software is becoming standard. The other problem is if you have 64-bit or 32-bit processor, the 64-bit software won't work in it. Okay, so you probably saw that when you were installing Eclipse. You had an option to go with, for your Java or your programs, an x86 and an x64. Funnily enough, the x86 is the 32-bit and the x64 is the 64-bit. So when you do see software available, look out for the 86. That's what corresponds to the 32-bit processing, okay, in terms of when software is being spec'd, okay? Right, so that's buswidth. Serial and parallel transmission. So this is really just theory stuff here about how data is transmitted. Serial and parallel. Okay, so serial transmission only allows one bit of information to go down a line at a time. Okay. And parallel transmission allows several bits, usually at least 8, to transmit at once. Why is 8 kind of a significant figure?
Double 4.
8 points is 1.
Yeah, two nibbles are a byte. Okay, 4 is a nibble, and 2 nibbles is 1 byte. Okay. So rather than sending a 1 and then a 0 and then a 1 and a 0 and a 1 and a 0 and a 1. Okay, you're sending all those 8 together in one chunk. Okay, so that's serial transmission versus parallel transmission. Okay, that's the difference between serial and parallel. Next bit I'll look at is synchronous and asynchronous. If I was to say to somebody, synchronize your watches. Okay, so I want Jamie and I want Chris to synchronize your watches. What would you do if I asked you to do that? What? Same time, right down to the second.
Brilliant. Right.
Yeah.
The last one, serial and what was the last one called?
And parallel. Parallel, yeah. If anyone is a fan of the old A-team like myself, they used to always go off on a mission, and before the mission they'd be synchronizing their watches. So they, what? I have with Liam Neeson, yeah. Charlie's trying to get me off task here.
Some of them films. Love when the guys spin round helicopter. Spin me right round.
Right. Moving swiftly back to, hopefully the cough will start taking over again. Moving back to synchronous transmission. That sends data in one long stream or block of data, so there's no gaps. I'm going to show you a diagram about this in a second. Data is sent one bit after the other. The receiver counts bits and reconstructs bytes, so it's essential the timing is maintained. It's normally used for internal data transfer within a PC. So that means data transfer on the motherboard. The motherboard is synchronized on the clock speed of what? Of the processor. The processor is a clock speed, which we talked about a minute ago. 2.6 gigahertz might be the processor speed. So all the transmission of data is synchronized to that speed. So you don't think about when does the data begin or end. You know that if I'm transmitting data on this clock cycle, it's going to arrive at that clock cycle. You know, it's going to arrive on the train, if you like. With asynchronous communication, the receiver must have a way to distinguish between the valid data and the noise. So in computer communications, this is accomplished through a start bit and a stop bit. Okay, so if you're on your walkie-talkie, how do you start the conversation?
Over.
Yeah, over. Okay. I'm giving you a message, over, so you know when it starts and it stops, okay? So asynchronous transmission is usually from one device to another, and the device says, because the two devices may have different timing, you'll be able to say, this is where I start, this is where I stop, okay? And here's your chunk of data, and it knows then, even if it's on a different timing, it receives the data, it gets the start of the data, and it knows where the end of the data is as well. So I'll just read through there what it says. With asynchronous communications, the receiver must have a way to distinguish between valid data and noise. In computer communications, this is usually accomplished through a special start bit and a stop bit at the beginning and the end of each piece of data. So for this reason, asynchronous communication is sometimes called start-stop transmission. Most communications between computers and devices are asynchronous. Okay, it's only really communication on the motherboard itself that will be of the synchronous type. So just a diagram there of what asynchronous and synchronous data looks like. Should this, in the very likely event of this coming up in the exam, I would say the best way of understanding this is to know the diagram, and then if you draw the diagram, you should be able to talk around what's on the diagram. I think that's a good way of remembering asynchronous and synchronous. And serial and parallel as well. In the video recording here, I've drawn a little diagram that you'll be able to see if you review the video of the lecture that I'm doing. Okay, so there's the diagram of that. Overclocking. Sometimes we overclock, do we? So that's the process of making a computer or a component to operate faster than is specified by the manufacturer. Where's Roy? Do you ever overclock your car down Mulgrave Street? What? Tell me what you do to overclock your car, or what would you mess around with to make her distributor, right? So it wouldn't be unlike getting your CPU and making it, you know, the manufacturer says this is how this should operate, but I want my car to sound louder or move faster or have higher revs or whatever you're messing around with. Overclocking in terms of PC manufacturer can be achieved by increasing the multiplier rate. So if you look up the motherboard specifications, there should be jumpers there to increase the multiplier rate, and you can increase the front side bus speed by changing settings and the motherboard setup screen then as well in the BIOS. Disadvantages, advantages, of course, your computer should zip along faster, okay? Not really an issue nowadays. Overclocking was probably something that was done to computers by people in the 80s and the 90s, where really you could see a significant, you know, difference by changing these specs. But nowadays I think computers really are quick enough to do what we want them to do, typically. And you can buy more power as well if you need more power more easily nowadays. Disadvantages of doing it, if it's something that you want to do it can cause overheating. And I think that's obvious. If you get something running higher than the specs or quicker than the specs, that means that the CPU is getting hotter than the fan that's spec'd against it is able to cool it. So you're going to have issues there. It can decrease reliability, and you may run the fan into overdrive trying to cool things down as well. Okay, that's pretty much